Okay, to everyone's attention, I want to introduce our speaker for today. This is Dr. Kramer from the Lunar Planetary Institute, which is basically right over there. We're going to be neighbors with them once we move to the new physics building next summer. Dr. Kramer studies the composition, structure, and evolution of the moon, asteroids, and other planetary bodies using data from spacecraft missions. She was a member of the science team for the Moon Mineralogy Mapper, which is the first instrument to unambiguously detect water on the moon. She's also been with the Lunar Planetary Institute for 7 years now. So, longtime neighbor, knows, she's seen a lot about what's going on with this campus, I guess I'm not too far away. So also Lunar Planetary Institute, I should mention that they do have a summer internship program.
Yes. So
maybe if there's something you might be interested in, this is someone you can talk to. Turn it over to Dr. Kramer.
Okay. Well, I hope you guys enjoy this presentation. This is my favorite subject. Has anybody here ever heard of lunar swirls? Yeah? Okay, that's great, because most planetary scientists haven't even heard of them. If you study the moon, you've probably heard of them, but other than that, they're a pretty weird thing. I do want to say that I'm kind of notorious for not realizing that I'm speaking jargon, so please do not be afraid to stop me and say, I don't know what a basalt is, George, or something like that. And you can call me George, too, by the way. Just put your hand up, let me know. If you have a question in the middle of it, I'm okay with being interrupted, okay? So I'm beginning with an outline of the presentation. I will first do a nice little introduction to our moon, that is a capital M, because it is our moon. And then I'm going to give you a little introduction into spectroscopy, reflectance spectroscopy. And then I'm going to introduce the concept of space weathering. This is a little different than space weather. This is space weathering, like erosion and weathering happens on Earth, but it's a little different on the moon. And then I'm going to talk about how I use impact craters to look through the soil on the lunar surface and see the composition of bedrock. And then how I kind of discovered swirls, again, not really myself discovering them, but saw them and appreciated them. And then I'll talk about some of the swirl science, some of the work I contributed to lunar swirls, and conclusions. Okay, so what is the moon made of? No. It is actually made of pretty much basalt. The mare are made up of this rock type basalt. It is the most common rock type in the solar system. It makes up all of Hawaii, the Galapagos Islands, and all of the ocean floors. It's all over Colorado, India. It's all over the place. It's all over Mars. It's all over Venus, probably. And on the moon, it is definitely where these dark areas are. The brighter areas we call the highlands, and they are made up almost exclusively of one mineral type, which is also a common one that's in basalt, but in this case it's just one mineral type, and it's called anorthosite. Anorthosite is a bright mineral, and that's why the highlands are so bright. In fact, on this near side of the moon, about 50% of that surface is dark. 50% of it is bright, yet when we have a full moon, that is a very bright feature. Has anybody here seen the far side of the moon, what that looks like? This is the far side. It would be a really bright moon if we had that facing us, which geophysicists tell me was just as likely as the side that's facing us now. This is a bit of a diversion, but I think it's cool, and I'm trying to propagate this knowledge or this history. In the, I think it was 16th century or 17th century, when Giovanni Ribisi and Francesco Grimaldi were mapping the lunar surface for the first time using a telescope, they were naming these mare features, and I forgot to say they're called mare because they resemble seas. Not that they necessarily thought they were water, but they called them mare. They named them for this old proverb that stated that when the moon is waxing, the weather on Earth would be pleasant, that the moon's phases controlled the weather on Earth, and that when the moon is waning, It will be stormy, rainy, and generally unpleasant. So we have things on the waxing side like Mare Serenitatis, the Sea of Serenity, and the Sea of Tranquility, and fertility, and nectar, all wonderful things. But on the waning side, we have the Sea of Cold, and the Sea of Rain, and the Ocean of Storms, and the Sea of Moisture, and the Sea of Clouds. So, some reflectance spectroscopy. And reflectance spectroscopy meaning that I am looking at these spectra that are coming from a external light source, is shining on the material, and the spectra the light is reflecting off and shining back to the optics. So my light source is the sun. It interacts with atoms and minerals on the surface of the grain, and some of the photons will get absorbed at specific wavelengths depending on the composition. Some will get transmitted through, some will get reflected back. And now we have our spacecraft or observer out there in space, and this light is diffracted, is reflected first, goes through the optics, is diffracted into its component wavelengths, and then we take away the spectrum of the sun, because it does have its own spectrum, and we get what is called a reflectance spectrum, and that is showing us what got absorbed and what got reflected back from the sun. And we get these plots, which shows the wavelength of light over versus reflectance, and we get these squiggly lines. And these squiggly lines are useful because the location of the squiggly line will show us, or it tells us how bright it is. Its shape tells us, meaning like if it's flat or it's sloped, is also telling us something about its composition. And most importantly are the absorption features, which are the dips in the squiggly lines, occurring here, and much more obvious in these ones. So these four minerals here are common, actually five, excuse me, are common minerals that make up a basalt. Olivine is a green mineral. These are two different kinds of the mineral pyroxene. This is plagioclase, that's that anorthosite, that highland mineral. And this one down here is ilmenite. It's a very dark black mineral. It absorbs a lot of light. So we can use the shapes of these spectra to get at the chemistry that's going on the surface. So even though we have only landed in, well, I guess technically 9 locations where we've returned samples, 3 of them were Russian and 6 of them were American. And they are all clustered like right around in these kind of areas here. Oh, somewhere over here. We actually can map the entire surface based on the squiggly lines for at least 2 chemicals. 2 elements, or their oxides rather. Iron oxide, and again we used the stations where the samples were taken as calibration points. And then we're able to use it across all of the lunar surface. And also a map of what the titanium oxide limit is. Ilmenite is the carrier of titanium on the moon. Okay, so as I said before, space weathering is more like the weathering and erosion that goes on the lunar or on Earth's surface, which is due to wind and water and geology, geologists tracking all over the place. On the moon, it's very different because there's not at least that much water, and there's certainly no wind, but there is a kind of wind. Anyway, what it has comes down to about, space weathering comes down to like 2 things. And it is what makes the surface age. And these are meteoritic bombardment and the solar wind. So the meteorites, and here I'm talking about macrometeorites, but also micrometeorites, so things that could be like the size of a grain of a dust grain. And it hits the lunar surface, there's no atmosphere to stop it, so it just gets right through, and it is going to physically melt and cause a reaction to occur. And out of it you get things like soil, you get the breaking up of rocks, and it turns into soil, or what we call regolith, and glass from melting. And then you get this other thing I put in quotes as big iron. So this is more of the line between physics and chemistry is going on right here with respect to micrometeorites. Because these little dust grains, they come in with all of the force that they started with, and they can actually cause, they can actually sputter, they can actually, or they can cause a little bit of melting to go on and a bit of a chemical reaction to occur. And all of that iron oxide that might be in that mineral reacts, and the oxygen gets liberated, and you get left behind with these iron blebs. They have no valence state. They are metallic iron proper, but they're really tiny. But I'm calling them big iron here because they are bigger than 50 nanometers. That's big. And right, the spectral effects is, by mixing, I mean that the different minerals and compositions are getting mixed, and so the spectra wind up becoming a mixed spectrum. And by darkening, this is what's important about these larger small iron blebs, nanophase iron blebs, is that they have this effect on the spectrum of taking whatever that spectrum is, the highland, the fresh basalt, and just darkening it across all wavelengths. On the solar wind side, since all it can really throw is, well, for the most part, protons, a little bit of helium ions, and then some photons, of course. But this is when these protons, which are the things that are actually having the most of reaction, interact, they can sputter, they can cause a chemical reaction, or they can be the agent of a chemical reaction by introducing hydrogen into the soil. But solar wind is mostly responsible for creating little iron, or little smaller than 50 nanometer size iron particles. And these particles have, which can grow, that's right, by micrometeorite bombardment. But these little particles have the effect on the slope of reddening it. So there is a general darkening across all wavelengths, but what is being shown here is the darkening and the reddening. So what is a slope that goes like this here for the mare basalt is now becoming red. It's becoming a tilted slope. So really what's going on is more that, like, there is small and big nanophase iron being created, and the little nanophase irons are doing a lot more darkening in conjunction with the bigger nanophase irons. They're having a stronger effect on the shorter wavelengths. So similar to the way that we can use the spectra to identify minerals, and since we know their composition, we can therefore get the chemistry of the entire lunar surface. We can use the effects that they have on the spectra from weathering and create a map of the maturity of the surface. So I just talked about space weathering. Maturation is the evolution or aging of the surface material, right? Like all of us, as we're growing older, we're maturing, we are growing older, but here maturity is a measure of that maturation. So here this would be like how many wrinkles are on your face, or age spots, or what have you. Optical maturity is a measure of the maturity using spectroscopy. There are other methods. You can actually measure in the sample the amount of nanophase iron as a ratio of the remaining iron oxide, and that is a measure of maturity. But optically, just using optical parameters, just that reddening of the slope and darkening is the optical maturity measurement. And this is a map of using that of what the maturity of the moon looks like, where all the bright areas are immature areas. And you can see this is Tycho. I'll back it up a little here. Tycho crater is about 180 million years old. And you can see its ejecta rays still existing. They're still bright. Jackson, which is back over on the far side, is another very fresh crater. Okay. So just like these craters that I just showed you, Jackson and Tycho, they expose fresh material, and this material comes from underneath that surface regolith. So in comes an impactor, and it plows into the ground, but more importantly than just digging a hole, it actually causes an explosion. So out comes this material from underneath, and it goes up, out, and over, so that now you have fresh material overturned right onto the surface. So I actually use that fresh material that has just been overturned right on the rims of the surface to look at the composition of the material that it's exposed. Because that regolith, that soil that's everywhere, is just mixed up material over billions of years. So the composition is not, you can't really see what's going on. But I look at these fresh impacts to get at the composition of the fresh bedrock. And I used to have a little animation here, but it disappeared. And what it would show you is little circles appearing around all of these little fresh-looking impact craters. And in this way, I'm able to actually make a map, and I was able to determine that these were each different units, basaltic units, and map their relative ages and compositions. Not as they appear on the surface, because just from the surface, they don't look quite that divided. And so I go about mapping the front side of the moon in this way. This isn't really my map. This is it's just a nice demonstration of the kind of thing that can be done. Then I went to the far side, and since I'm used to mapping mare basalts, I went for this huge region over here. This is the largest impact basin in the solar system. Don't let any Martian tell you differently. And trying to map some of the mare here, and I went for this place right here called Mare Ingenii, the Sea of Ingenuity. And I'm looking at this thing, and I am a trained lunar scientist. I've heard of lunar swirls, but I just didn't really appreciate what a pain they are. Can you guys see them? The lunar swirls? Yeah, they're like these trippy little things. You know, like that's an impact crater, that's part of an impact crater, but these things are different, and they're weird, and they are not behaving according to physics, as far as I can tell. So, what are lunar swirls, you're asking, right? So lunar swirls they're high albedo features. Oh God, I'm sorry. Okay. Lunar swirls are high albedo features. They usually have a sinuous shape and interweaving dark lanes. They are always associated with magnetic anomalies on the moon, and this is very important. The moon, yes? Oh, sure. Albedo is, it's the reflectance, it's the brightness. And sinuous is curvy. They're like snake-shaped, often. There is a couple of them that are more diffuse looking, but so the moon has no global magnetic field the way that Earth does, or even Mercury. But it does have these discrete areas of remnant magnetism that nobody has been able to explain why they're there, but they are, and associated with most of them, you can find lunar swirls. Oh, that's right. The swirls also impart no topography. They just drape over whatever topography is there, if it's flat or if there is a hill, and they look fresh. So, yes, here's the explanation of how the moon does not have a global magnetic field. So here is a magnetic field strength of the near side and far side of the moon. All these purple areas are basically no magnetic field to speak of. And then you have anything that's deviating from blue or purple is areas where there is an enhanced surface magnetic field. And where these squares are appearing are known lunar swirl locations. So it is important to say that although every swirl is associated with a magnetic field, not every magnetic field has a swirl. Another weird mystery that we're working on. So I say that the swirls impart no topography. This is Rainier Gamma. It is the probably most popular swirl because it is on the near side of the moon, over here in Oceanus Procellarum, so it is the best known swirl. You can look at it through your telescope. People have been looking at it for a while. And here is a series of images from the Kaguya, the Japanese mission to the moon from the early 2000s, where it's zooming in and zooming in and zooming in, and you can see that it's just flat. You can even see the craters start to appear, but the swirl features themselves are just laying there. Right, so the swirls are optically bright and are bright and optically mature. They have a high albedo and they're immature. And these three swirls here I'm showing are kind of meant to show the kind of type locations on the lunar surface you can have. You can have just mare basalt, so there's a dark area, and there's the swirl Rainier Gamma. This is the area called, I think, Gerasimovich. Does anyone here speak Russian? I cannot remember if it's a hard G or a soft G, but I think it's a hard G, Gerasimovich. And it is all in the highlands area, so it might be a little difficult to see the swirls, but you can see some here, here, over here, and over here, and a little one like right there. And then Mare Ingenii, which I showed you before, which is mare and highlands. in fact, the highlands continue to extend up and further towards the north and east. Oh, and this is where they're located. And this is what they look like in optical maturity. So now you can see it's a little bit easier maybe to see the ones in Gerasimovich and kind of in Genii. And you can also see all of these little circles are fresh impact craters. So there are basically two hypotheses for how the swirls are formed, or what they're doing there. The first one is a comet impact. And this one is postulating that the swirls are actually immature. They are actually a recent event that occurred. And it explains why they look bright, it explains why they look immature, and it explains the magnetic anomaly. And this explanation is that as the comet is impacting onto the surface of the moon, it has a coma. It sets up a temporary atmosphere. There is turbulence, which can create the swirly features. And the pressure that is occurring and the heat that's being generated creates a plasma. It interacts with the interplanetary magnetic field coming from the sun, and it basically imparts a magnetic field onto the surface. The other hypothesis for its formation is the deflection of the solar wind by the existing magnetic field. So in this one, there's a magnetic field, which I am representing here with this white thing. It's just supposed to represent the magnetic field, not the swirl itself, at least yet. Oh yes, I'm sorry. It's a deflection of the solar wind by the magnetic anomaly is preventing the normal maturation process. As you remember, I said there's micrometeorites, so there's meteorite bombardment, and there's the solar wind. The solar wind is mostly protons, so it can be influenced by a magnetic field. So in this cartoon here, the salts have now flooded over it, and as time goes by and the basalts mature, this area where the magnetic anomaly is stays immature looking. And in this hypothesis, the swirls are not actually fresh features. They only appear fresh because the magnetic field is deflecting the solar wind. It explains their brightness. It explains why they look immature. It explains the magnetic anomaly. I won't get into how that one, this theory actually does have an accompanying theory for how the magnetic anomalies got there, which I'm not going to get into. I don't care, because they're there, that's all I care about. It also explains why they don't impart a topography. And it's also the only one that explains my observations, which I'm going to go into now. Okay. So I contributed 3 major results to support the hypothesis that the magnetic field is deflecting the swirl surfaces and keeping the swirl surfaces from maturing at a normal rate. Oh, and also, yeah, mostly importantly, I really feel strongly that I disproved the comet impact theory, or hypothesis. Okay, so I showed that the density of the fresh impact craters, you know, those are the ones that I use to look at what the composition is of the underlying material. I showed that the density of those fresh impact craters on swirl versus off, I'm sorry, what am I writing here? My contributions were to show the density of fresh, well, what I did, I'm sorry, was to show that the density of fresh impact craters on the swirl compared to off were much higher than those compared to off-swirl. I know that sounds really confusing. I screwed that up. It's okay, I'm going to do it. I'll get into it in a minute. I also looked at the spectra of fresh craters and compared them with the mature soils on the swirls and off the swirls. And then I also looked at the hydrogen, or rather hydroxyl OH, or maybe water, abundances on the swirls and off the swirls. Okay, so mare and Genii again. This series of red dots is showing you the distribution of fresh impact craters that I looked at. It was completely independent of whether it occurs on a swirl or not. It was just based on some threshold maturity parameter, I said. They all needed to look like they were more immature or fresher than this, the brightest swirl surface. And the distribution looks pretty random, right? And this is what you'd expect, because impact cratering is a random process. So then when I mapped the swirls afterwards and then counted the density of these fresh impact craters that occurred within the swirl boundaries and compared it with those that don't occur on the swirl boundaries, that is either in the dark lane areas, which is between swirls, or even just kind of outside the mare area in general. There was 4 times as many impact craters on the swirls as off the swirls. Now, it might seem at first that that's saying, oh, well, there must be something that's attracting those impact craters to the lunar swirls. But these are large impact craters. They're greater than 100 meters in diameter. No magnetic field is going to affect these impact craters. And in fact, no magnetic field would even be affecting a piece of dust. This is actually because where those swirls are, that magnetic field exists and that surface is being protected, so these fresh craters keep looking fresher longer. Then I compared the spectra of the craters on the swirl, these fresh craters on the swirl and off the swirl, as well as also comparing them to their mature, if you will, surface. And I put mature in quotes because when you're looking at the mature soil on the swirls, it doesn't look very mature. So all of these dark lines are fresh craters that are not on swirls. All of the white lines are fresh craters on swirls. The dashed line is an off-swirl mature soil, and this white dashed line is a mature soil on swirl. It is not, it is, I guess it kind of is a coincidence, or it's not, I'm not sure, that all of the off-swirl spectra are all darker than all of the on-swirl spectra. Again, these craters were selected before I ever mapped which was a swirl and which was not a swirl. So it is not like I made this division based on where this, I said, okay, all of these are going to be off-swirl and all of these are on-swirl. No, they divided themselves. It's hard to tell here, so hopefully I have, okay, fine. So all of the spectra that are occurring on the swirls actually resemble fresh crater material. And that kind of includes the soil. It does look a little mature, but nothing like a normal soil. A normal soil on the moon, which is more like this dark one. And also, most importantly, is that all of the fresh craters that are off the swirl look like they're already kind of mature, in fact. But mostly, they only look like they're darkening. They don't look like they're reddening. Then I looked at the compositions of these fresh craters, the iron and the titanium. And I'm just going to skip the iron one because the titanium one is where it gets really exciting. I don't know how many geologists are in the room or lunar geologists are in the room, but on the moon, the mineral ilmenite, as I said before, is the carrier of titanium. The mineral ilmenite, it's not a common mineral on the Earth's surface, but on the moon it's not uncommon at all, but it only occurs in the mare basalts. So if there's going to be ilmenite, meaning high titanium, it's going to be coming from the mare basalt. So looking at this map here is showing the surface titanium abundances. And all of the spots that you see are those fresh craters and what their composition is. So what's weird here is that of all of the fresh craters, the highest titanium abundance that you can get is 3.5. But the highest that occurs on the surface is 8. That's not possible because that titanium has to be coming from the mare basalt. So it has to be that the higher titanium value would be in one of the fresh craters, not on the surface. Because that surface is a mixture of stuff from way outside, the highlands mostly, because that's what's surrounding it, and it has no titanium. So this is very strange. And that's when I noticed that these areas that come up as white, coming up with these really high abundances, absolutely correspond with the dark lanes. So I said to myself, something is tricking the titanium algorithm. What does the titanium algorithm do? And I don't think I put it in here. Did I? I'm sorry. Yes. Okay. The titanium algorithm is basically searching for a spectrum that is dark and flat. And it says, if I'm seeing dark and flat, and whether it's mature or not, I can actually ignore that part. I'm looking for dark and flat. If it's dark and flat, it's a fresh ilmenite. So it's going to have a high titanium value. The other thing that's dark and flat is little iron. Excuse me, big iron. So that's when I realized that this surface is not full of ilmenite, it's full of a bunch of big iron. It's being matured really fast, and a lot of nanophase iron is being created quickly. I should have shown you this before, sorry about that. This is nanophase iron, these little black blebs inside of a soil grain, and there's a scale bar. The third thing that I contributed was to look at the hydroxyl or water abundance on the lunar surface. The Moon Mineralogy Mapper was the first instrument to detect this and actually map it globally. And we saw it everywhere, completely unexpected. It would occur everywhere except right where the sun was shining, meaning that it would stay persistent at high latitudes above 60 degrees. It would fluctuate with the lunar diurnal cycle, meaning that at sunrise, as the increased solar energy would start to drive off any of the water or hydroxyl that might have formed at the surface. At noon, there was a maximum loss, but again, just in these more equatorial latitudes. And then in the afternoon, the hydroxyl water would start to stick again and probably stay on through the night, but it's reflectance spectroscopy, so we can't really measure what's dark. So this like cycle of like moisture forming, and then the sun rises and it burns off, and then the sun sets and the moisture comes back. Does that remind you of anything? Like what?
Well, I guess
yeah. Well, so I'm thinking of dew, right? And so I'm really looking for somebody to help me market the next space mission to go check this stuff out in more detail to Mountain Dew. I think that this is a really great idea. Okay. So here's these three swirl regions, Rainer Gamma on the Mare, Gerasimovich on the highlands, and then Mare and Genii on both. But this is now mapped with the Moon Mineralogy Mapper data. And just like you can make an optical maturity map or an iron titanium map from the data, the Moon Mineralogy Mapper was able to go out with enough with a good enough spectral resolution out into the 3-micron region to actually observe this absorption feature due to the presence of hydroxyl or water. And I keep saying hydroxyl or water because the instrument wasn't good enough to detect the difference between them because that absorption occurs very close to each other. The point is that it's water related. So anyway, so we could make a map of that relative abundance, and this is what happened. The swirls are perfectly outlined, better than any map I've been able to see so far. You can see the swirls at Gerasimovich much better, and you can also see that the ones that are out into the highlands and Genii, and they actually, again, do extend up further, but at the time I was doing this, I wasn't aware of that, so I had cut my boundary off. And they appear dark because they have a lower hydroxyl or water abundance than their surroundings, because there's not enough hydrogen making it to the surface because it's getting deflected by the magnetic field. So, in conclusion, weathering is retarded on swirls, and I got to publish that in 2 papers. The swirl surfaces resemble spectra, spectrally resemble fresh material, even on their mature surface. The density of immature craters that occurred on the swirls were 4 times that of off of the swirls. The hydroxyl is depleted on the swirl surfaces. And this supports the solar wind deflection model. And it can all explain, this can all be explained by the solar wind protons being deflected by the magnetic field and limiting space weathering just to micrometeorites on the swirl surfaces. And also what I showed was that weathering is accelerated off the swirls because all of those off-swirl fresh craters look really dark and flat. So it looks like they actually mature quickly. Right, and that the dark lanes are not rich in titanium, but rather they're just rich in nanophase iron. And so now you know the swirls provide a laboratory to study the solar wind, space weathering, and complex electromagnetic interactions, and on a scale that we can't do in between being a laboratory or being a global Earth magnetic field. And again, I tell you to go out with your binoculars or telescopes and look at rain or gamma when the moon is waning. And also this concept of space dew, which is a solar system-wide process. It's not just occurring on the moon, it's probably occurring on asteroids, and it actually could be a viable process for which we could actually be extracting water, or at least looking for reservoirs. And that's it.
Questions? What was that relationship between the magnetic fields and the swirls again? You said it's like if there's always a magnetic field, there's a swirl.
If there's a swirl, there's a magnetic field, but there are some magnetic fields that don't have a swirl. In fact, there's one like kind of like really big, whopping, glaring one for me in this mare region, where there's actually two magnetic anomalies in the one mare, one in the north and the south. And I've tried searching in detail, trying to find something, stretching the data as much as I could. More recently, the ultraviolet camera, or one of the ultraviolet instrument on, there's two, I'm sorry, on Lunar Reconnaissance Orbiter, they've been able to see the swirls. And what's interesting is that the UV is very sensitive to maturity, and the swirls are kind of the only thing that keep looking immature in UV light. Like even Tycho disappears. So it's another hopefully way we can, data set that we can hopefully stretch and play with and look at in these particular places where we're not seeing the swirls, and maybe something will appear. Or we have to explain why that's not happening. Okay. Ingenia. Ingenia, yeah. There's a lot of reasons. It's in South Polakin. South Polakin is this largest impact. It's about 4.3 billion years old. It's never been sampled, and it is actually like a #1 priority targeting location for returning samples back from the moon. And if we went to Mare Ingenia, we'd be in South Polakin, so we could get South Polakin samples, and we could also be landing like right on one of those very sharp boundaries and be getting mature stuff and immature stuff with just a lander. I have an entire presentation all about why we should be going to Ingenia. Yeah, there's three different instruments that have measured it. Two of them globally. There's the Kaguya mission, the Japanese mission Kaguya. They measured it. The Lunar Prospector mission actually measured it with two different kind of techniques, and Apollo missions. I think two of the Apollo missions measured some of them, but it wasn't a global measurement because it was just while the capsule was flying over, waiting for the people on the surface to come back.
You kind of answered part of it, but one of the first charts, graphs that you showed at the beginning, that I think was your opportunity graph that plotted reflectance and the number. What were those first ones in your minds? I heard you say UV to your internet. Is most of that optical, visible?
Yeah, I work in the UV to UV visible and near infrared out to about 3,000. Yeah.
Have a hydroxyl and water of that. What's the concentration in the explosive that you registered? Say pressure or column pinch or something? Or is there any way to quantify that?
Yeah, it's really, really complicated. And personally, I hate to try to get into quantifying it because there's so many unknowns. The spectrometer itself is there's so much noise associated with it, especially in that region, so much uncertainty that quantifying it is, in my opinion, fruitless. But people have made attempts to quantify it, and I think that I'm trying to remember. I think that most of it was coming up in between 1 and 8,000 ppm.
Is there any indication whether the reservoirs you can see, it's causing
the sun. I think the sun. The sun is.
So it's bars under the material from the sun.
Yeah. It's storing hydrogen at the surface. And actually, a project that I'm working on now is looking at how the soil is retaining that, how well it's doing at retaining it as it ages. Is it actually retaining the hydroxyl as better as it ages. That sort of says something about how it's being retained. Is it being retained in the glassy soils, or if it was being retained better in the fresh surfaces, then that just might be like a kind of van der Waals bond attraction between the surface minerals and the protons.
Instead of, say, a comet, say you had an iron meteorite that struck the surface, would that cause a magnetic anomaly? That's
actually a pretty recent paper by, his name is Mark Wazorik, and he noted that on the far side, at South Polakin, that's where the largest spread of strongest magnetic fields is occurring. And his hypothesis is that the impactor that created South Polakin was a differentiated meteorite body, and that it imparted it just through its core all over the surface of the moon.
Any questions? All right, let's thank our speakers. And I want to remind you guys, next week we're going to have Stephen Kuntz is going to be here talking about the International Space Station and spacecraft charging, some of the hazards associated with that. Also, I do have a couple more papers if you guys can grab them. So, see you guys next week.